everyone to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim R&D Manager and the Associate Director of our National Center for Simulation in Rehab Research. I'll be serving as the moderator for today's webinar. I'm pleased to welcome today's presenters. Colin Smith, Daryl Phelan, and Christina Cook are joining us from the University of Wisconsin in Madison, and they'll be telling us about enabling stochastic simulations of movement with high-throughput computing. Next slide. Before we get started, for those who are new, OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating the movements of humans and animals. So the first goal of our webinar series is to showcase the many kinds of cutting-edge research that's being performed with OpenSim. OpenSim is also a growing and geographically diverse community of users. I think we have over 150,000 downloads of OpenSim now. From all over the world. And so the second goal of our webinar series is to provide an easy platform so all of you in the OpenSim community can communicate and form new collaborations. Next slide. Before we get started, a couple quick reminders about the format of the webinar. We definitely want to leave time for your questions, but we'll take those at the end of the talk using the text-based Q&A panel in your WebEx interface. If you need any additional technical help, you can send us an email or consult the guide on our website. So now I'd like to go ahead and introduce our speakers. So next slide. Oh, well, we'll imagine that first slide again. So our speakers today are, first we have Daryl Phelan. Dr. Phelan has been on the faculty of the University of Wisconsin-Madison since 2002, and he's currently the Harvey Spangler Professor of Engineering with appointments in the Departments of Mechanical Engineering and Biomedical Engineering. His research interests are in the field of neuromuscular biomechanics broadly. His current projects involve the use of computational dynamics, controls, and dynamic imaging to investigate the influence of injury, aging, and treatment on musculoskeletal function and health. His research activities have been supported by the NSF, the NIH, and a number of private foundations. Daryl is also joined by Colin Smith. Colin is currently a PhD candidate in the University of Wisconsin Neuromuscular Biomechanics Lab. His research focuses on simulation and imaging of knee mechanics during movement to investigate the etiology and treatment of osteoarthritis. We were pleased to host Colin as a 2016 NCSRR visiting scholar, and he's won multiple awards at international conferences for his simulation research. And then third, Christina Cook. Christina has been a research computing facilitator at the University of Wisconsin-Madison since November of 2014. In this role, she assists researchers on campus in using the large-scale computing resources available to them through the Center for High-throughput Computing. Christina comes to research computing from an academic background in mathematics and diverse experiences in computing, education, and online collaboration. So we're thrilled to have you guys today as webinar presenters, and with that, I'll let you guys kick it off.
Okay, so this is Daryl, and I'm going to start this off. So I want to first thank Jen and Joy for organizing this webinar. We really appreciated the opportunity to put together these materials. This is stuff that we've been working on for a couple of years now, and this allowed us to put it together in an organized way and share it with you and hopefully get some feedback from you as well. So many of you are involved in biomechanics currently and are aware of some of the things you can do in movement biomechanical analysis. Some of these techniques, OpenSim has really extended the use of computational tools in biomechanics. But a typical approach is shown here, where in a motion lab you would record kinematics and ground reaction forces, and then you would use a musculoskeletal model to estimate a bunch of internal variables of interest, including muscle forces and joint contact forces and such. And this is a standardized tool nowadays that OpenSim allows you to do quite easily But one of the things important to recognize in this is that there are a number of assumptions that lead to uncertainty in the final predictions. So on the measurement side, marker placement, soft tissue artifact, and noise. On the modeling side, you're making choices on the number of segment joint degrees of freedom, geometry, and muscle tendon parameters. And then in the analysis phase, you're also making assumptions regarding the scaling of a model, marker weights and inverse kinematics and anthropometry, and then importantly, the objective function that you use to resolve the classic muscle redundancy problem. Now, Bradley Davidson and his group at the University of Denver a couple of years ago gave an OpenSim webinar, and they developed a nice plugin that you can use in OpenSim to start to consider how uncertainty in some of these factors might affect your ultimate outcomes. So the blue boxes you see here on the left are things that are considered probabilistic variables, and you can use Monte Carlo type simulations to consider variations in those parameters and then look at how that affects your ultimate muscle force estimates in this case. So the results that I'm showing here are muscle force bands of 95% probability of the muscle force estimates given the uncertainty in some of these parameters. And these were computed using about 3,000 simulations on the same data set. At UW-Madison, we've been quite interested in kind of enhancing and extending the basic musculoskeletal models used in OpenSim, and in particular been focused on knee mechanics. So instead of the standard 1 degree of freedom knee model, we're using a 12 degree of freedom multi-body knee model. And we're particularly interested in using this to understand cartilage contact pressure during movement. So this is a framework that we put in place, and we'll show you a little more details in a minute. But running a simulation the way we do it now, it takes about a half an hour for a gait simulation. So if I were to repeat that Monte Carlo analysis on this in serial, that'd be about 1,500 hours to do 3,000 simulations, which as an advisor is a complete non-starter, given the rate we need to work at. So we came to the Center for High-Throughput Computing here at UW-Madison, and we were able to put in a process in place where we could farm this out and do about 3,000 simulations in about 2 hours by doing them all in parallel. And so we'll show you some details today in terms of how you can do this yourself with OpenSim models. And at this point, we're going to have a real-time demo, and Colin's going to talk for a minute and actually launch 3,000 simulations on the Open Science Grid while we continue the webinar.
Okay, so we can get into the details of this a little bit later in the presentation, but the Open Science Grid is a high-throughput computing platform that's hosted on campuses all across the U.S. So I can log into this computing grid just using a web browser. So this isn't showing up especially well, but if I log in with my username and their login portal works for me, there we go, and put in my password. I have a personal account on the Open Science Grid, which all of you can do as well. And so just by typing one command, since I've already set everything up for this, so condor submit, and then my submission file, I can launch 1,000 simulations onto this high throughput computing grid right now. So we just submitted 1,000 simulations, and we'll come back and check on them at the end of the webinar. So now I'll hand back off to Daryl.
Okay, so we have those results to look forward to in a few minutes. But the rest of this webinar, what we're going to talk about is I'm going to give you a little more details on the knee model and some of the solution techniques that we use for that. Then Colin will step in and he'll show you some applications of the knee model in biomechanics. And then Christina's going to talk more about high-throughput computing with OpenSim. And actually, Christina will introduce the high-throughput computing in the Open Science Grid. And then Colin will take it again and show you how you can run OpenSim on the Open Science Grid. So to start with, on the knee modeling side, I want to recognize that not all of you are interested in particularly working on knee mechanics right now, but hopefully you're interested by the end. But this is just showing you a standard knee anatomy, and the important point here is you have two joints, the tibiofemoral joint and the patellofemoral joint, and it's showing you on the right-hand side how we model both joints, and both joints are 6 degrees of freedom in this particular model. So creating this model, we started with MR images of a healthy young female, and we do the standard thing of segmenting out the bone segments and the cartilage geometry. You can then use an elastic foundation cartilage model to compute contact pressure based on overlap of cartilage tissues. And on the computational side, this is really why the simulations take a fair amount of time, is you need fairly high resolution meshes to represent the cartilage tissues. Ligaments are represented by bundles of nonlinear springs, and this is what passively constrains the motion. And then finally, we take that knee model and we plugged it into the standard Arnold lower extremity musculoskeletal model. So now you have a full 12 degree of freedom knee model incorporated in there. As far as actually using the model to do something interesting, the standard approach in OpenSim right now is to use muscle force optimization, where you would minimize a cost function to compute the muscle forces necessary to generate a set of measured accelerations. And that cost function is the sum of muscle volumes times activation squared. Now this approach works if your model is constrained to rotational degrees of freedom. The challenge we have is when you put in 6 degree of freedom joints, you can't use that base solution technique anymore. And here at UW-Madison, we introduced what we call concurrent optimization of muscle activations and kinematics. And I don't have time to go through all the details of what is happening here, but suffice it to say is what we're computing are both the 6 degree of freedom tibiofemoral and patellofemoral kinematics, while we're also calculating the muscle forces. And this is a loop, an optimization loop that's happening where you pass in the joint knee kinematics, and coming back are the contact pressures and the ligament forces. So you're solving both knee kinematics and activation simultaneous. And our cost function, we added one additional term, and that's a weighting factor, and that Colin will get into a minute why we put that weighting factor in. So what do we get out of analysis like this? Well, we get both the joint kinematics, but more importantly for us, we're also estimating the contact pressures, and you're looking down on the tibial plateau right here, and this is the contact pressures over a gait cycle, stance phase, I believe, right here. So that is highly relevant for those of us interested in causes and treatment of osteoarthritis. So one of the things you want to do when you create a model like this is to show that it has some physical realism. The approach we've done for validation here at UW-Madison is we have a 3D dynamic MRI approach where we can measure in vivo tibiofemoral and patellofemoral kinematics very accurately. So we track those. And then what we can do is simulate the exact knee flexion extension task that the subject is performing in the dynamic MRI scanner, and we can compare the kinematics between the two, and you can see in this animation here that they generally look quite consistent. Now, one of the things you want to consider in doing things like this is the approach that we use to create that knee model. We could reconstruct the geometry fairly well, but when it comes to material properties like the ligament stiffness, we actually don't have good measurements on what those are in vivo. And using assumptions from the literature, I could make a case for a very compliant ACL or a very stiff ACL. So there's uncertainty in here. Now, this simulation I'm going to show you here is a gait simulation with a stiff and a compliant ACL. And basically what it's showing is based on what I assume for that ACL stiffness, I get very different tibiofemoral kinematics during walking, and particularly during stance phase of walking, very distinct periods where you see differences in anterior tibial translation, as you would expect since the ACL is restricting that motion. So why is this important? Well, given that we have this uncertainty in this ligament stiffnesses, one of the things you want to consider is how might that affect the validation exercise that I went through previously. So we made assumptions on the uncertainty ranges for the ligaments in the model, and then we did Monte Carlo simulations on the high-throughput computing network where we randomly sample from these ligament stiffness probability density functions, and in the end we can create uncertainty bounds for our kinematic measures. So in this case, what you're seeing is uncertainty in the tibiofemoral kinematics as represented by the pink shaded areas. The red curves represent the nominal simulation, and then the black represents the actual experimental measurement. And the encouraging thing here is that when we consider the uncertainty in the ligament properties, all the actual kinematic measurements fall within our uncertainty bounds. So a conclusion you could make from that is we don't know what these ligament stiffnesses are exactly, but if we consider those the ranges that we think they're within, our measurements are within that range. So that gives us greater confidence in the validity of the model at that point. So with that, I'm going to pass this back to Colin, and he's going to talk about applications of the knee model.
Okay, so now that you've seen kind of the overview of how our knee model was constructed and how our simulation routine works, I'm going to walk you through 3 different examples where we've used high-throughput computing and probabilistic analyses to help answer research questions of our own. So first, we're going to look at ACL reconstruction surgeries. Then we'll look at the effect of neuromuscular coordination on tibiofemoral cartilage loading. And then we'll look at an example using statistical shape modeling with high-throughput computing. So first, we'll look at the ACL reconstruction. So the ACL is kind of the main ligament in the center of the knee. And in the U.S., about 150 to 200,000 people tear their ACL a year, usually young people doing sports. And so the common technique to fix that is ACL reconstruction. So they replace the torn ACL with a graft, and people return to normal healthy activity. But one of the big problems with this is that down the road, we see 10 to 15 years follow-up, you see high rates of osteoarthritis. And so what we're really interested in is how you can change this reconstruction surgery to improve the cartilage loading to hopefully avoid this osteoarthritis. So one of the questions that surgeons have to answer is where do they want to place the tunnels for the graft? And so specifically, we looked at the effect of the ACL attachment on the femoral side on knee mechanics. So we ran 2,000 simulations where we varied the femoral attachment of the ACL, and so it ends up resulting in these 60 to 90 degree angles for the coronal plane and 40 to 70 degree angles for the sagittal plane of the ACL. And this kind of spans what you'll see in normal and ACL reconstructed subjects. So we ran 2,000 simulations, and you can see the results of those for the stance phase here. So you're looking at the mean and the 95% confidence interval for the ACL force during the stance phase of gait. So you can see there's a pretty large variability depending on where you place that femoral tunnel. So if we analyze at this peak of ACL force, I can plot the coronal plane angle on the x-axis, and then if I plot on the y-axis the ACL force at this time period, and I scatter all 2,000 simulations, you can see that there's really a weak correlation between the two. However, if I plot the sagittal plane angle, you can see that there's a strong correlation between the sagittal plane angle and the ACL force. And this really agrees well with what we see clinically, where if the surgeon drills the tunnel too far anteriorly, resulting in a more vertical ACL in the sagittal plane, you see graft failures. So now we'll move on to the next application, which is looking at muscle coordination effects. So commonly in knee biomechanics, people will use the knee adduction moment as a surrogate for tibiofemoral cartilage loading. So you'll do gait analysis, you'll do inverse dynamics, and you'll get the knee adduction moment. And it's thought that that correlates well with the medial lateral distribution of the contact forces. And so there's been a lot of applications of the knee adduction moment, looking at OA progression, looking at gait retraining, how can you reduce the knee adduction moment, different insole design. But what this really factors on is that you're assuming that gait dynamics determine tibiofemoral cartilage loading. But from our model, we can see that there's other things that also factor into play in cartilage loading. So anthropometrics, constitutive properties, knee geometry, and then neuromuscular coordination. So that's what we'll look at a little more in detail here. So if we look at our normal COMAC simulation, you bring in your measured kinematics and ground reaction forces, but you also have to make an assumption of what cost function you're going to minimize. So what we've done is we've introduced this weighting term, W sub I, into our cost function. And so what that means is that if you increase that weighting term on a muscle, it will penalize its usage. So the optimization will solve for a muscle coordination strategy that does not use that muscle as much. Whereas if you made the W sub I smaller, then it would encourage muscle usage. So and this has really been shown in Scott Delp and Matt Demir's paper. So what we've done is taken a Monte Carlo approach to this. So we randomly sampled these muscle weights. We ran 2,000 simulations and then came up with kind of a family of muscle coordination strategies that can all generate the same movement. So if we look at these simulations, here I'm plotting the tibiofemoral contact force over the whole gait cycle. So you can see across all 2,000 simulations, you're going to get the mean and 95% confidence interval. There's a large variability in your predicted force at second peak. And so if we look more in detail at why this is happening, it ends up being a question of whether or not you're using uniarticular or biarticular muscles to coordinate this movement. So if you're using biarticular muscles, then sometimes you'll need to use the gastroc to develop an ankle plantar flexion torque that will also compress the knee joint, so you can drive up the tibiofemoral contact forces. And another interesting thing that we can use our model to look at is here, these are 5 pressure patterns all at this second peak of tibiofemoral loading, so at the same point in the gait cycle, just using different muscle coordination strategies. So these all have the same knee adduction moment. You're looking at the same point in the gait cycle, but you have vastly different cartilage contact pressures just due to neuromuscular coordination. So the last thing we're going to look at is statistical shape modeling. So this work has really been started by our colleague Allison at Queen's University. And so we started with 20 segmented MRIs of healthy subjects, and we built a statistical shape model. But in addition to kind of the normal geometries you include in this shape model, we have the bones, the cartilage surfaces, and then also the ligament attachments and their wrapping surfaces that all can morph. And we've kind of inserted that statistical shape model into our lower extremity musculoskeletal model. So what we can do is sample the statistical shape model, and we'll run thousands of simulations with various geometries out of the sampled statistical shape model. And now we can look at things like how does the geometry of the knee affect cartilage loading during walking. So here you're just looking at three simulations that have different geometries that we've generated using the statistical shape model. So now I'll just talk a little bit about where we see this going in the future. So we really would like to get more into this parametric modeling idea. So we know that we have all of these inputs of our model that affect cartilage loading. So if we can come up with distributions for each of these inputs, then we can sample those distributions and run stochastic simulations and come up with probabilistic predictions of cartilage loading. So one application of this would be population modeling. So if we parameterize a healthy population, like you see there on the top, and we parameterize an ACL reconstructed population, and then ran a probabilistic study, you can see that we get 2 different probability distributions. And maybe comparing these populations, you'd be able to gain insight into why one gets arthritis and one does not. Another idea would be to use a population model to predict kind of a generic population of results, and then you could use a subject-specific model to see where a specific person lies within the population. So perhaps they have a higher than average tibio-femoral contact force, and that might be what's causing them to get arthritis. So now I'm going to hand it off to Christina, and she's going to go through a little bit more in detail what high-throughput computing actually is.
All right. Hi, everyone. This is Christina, and as Colin mentioned, I'm going to be sharing a little more about high-throughput computing generally. You guys have seen already, Daryl and Colin have talked about how they've used high-throughput methods in their particular research and their approach. So I'm going to kind of give just an overview so you can understand what's going on if you'd like to apply this either to a very similar type of method or approach in your research, or if you see that your own problem could be addressed with a high-throughput solution. So just to recap what high-throughput computing is, it's a method to deal with a fairly common computational problem, which is that if you're running a lot of separate computational tasks and you only have one computer, in particular one like computer processor or core on that computer, it's going to take a long time because you're just going to have to run them one after another, and depending how many you want to run, that could be particularly lengthy. The solution is fairly conceptually simple, and that is to take all of those separate tasks and run them independently on a bunch of different computers or a bunch of different computer processors. In this transition, we usually refer to each task as a job. And if you can do this, you can see how it would take a lot less time to run the same amount of work because you're able to run things in parallel. So this idea of breaking up separate tasks into pieces and running them in parallel on separate computers is what we call high-throughput computing. And good high-throughput problems are those where you can indeed break apart what you're doing into a bunch of separate simulations. So what Daryl and Colin have been talking about is a perfect example because they just need to run many copies of slightly varying simulations. You don't want to run things that are too long, especially on the open science grid. 8 hours per job or per task is a good limit. And having software that's openly licensed and freely available is an advantage. If you need a license for every job you run, at some point if you're paying for that, it becomes quite expensive. So problems that don't work as well with this method are ones where there are things that can be run in parallel, but they need to communicate with each other, or you have strictly licensed software. So good high throughput problems, what Daryl and Colin have been describing, analyzing multiple data sets independently, using Monte Carlo methods, those all work really well. Typically, really large-scale physical simulations are not so good for high-throughput computing. So now that we know what makes a good high-throughput sort of problem, or problem that adapts well to this approach, why would you want to do that? I think as you saw in my little diagram, that one major advantage is saving time, running more work in less time. This approach also can allow you to take advantage of a lot of computing power. The open science grid is very big, and so it's very easy to scale up what you're doing because you'll be able to have more resources available to you. And that begs this final question: if you could run on, say, an unlimited number of computers, what would you change about your research? You know, could you improve what you're currently doing, or could you try something new and different? So those are all things to think about think about if this is for you. So how do we actually do this? There's a couple requirements for using high throughput computing methods. One, as I've just described, is a good problem, a good high throughput problem, and I've relisted some of the qualities there. And then the second is to be able to access lots of computers. It's great if you can break up your problem, but if you still only have one computer available to you, you're not going to go get very far. So you need to have access to many, tens to thousands to possibly hundreds of thousands of computers at once. So there are a lot of different resources to support these methods. In terms of accessing lots of computers at once, one option is local compute centers at your institution. So here at UW-Madison, we have the Center for High Throughput Computing. And there are other, which serves campus, and then there are other departments or groups that have their own resources. So this will probably not apply to a lot of you because you're not here at UW-Madison, but it's worth asking your sort of local IT staff if this is something that's available. And then there's also a national computing grid called the Open Science Grid, which Colin has already mentioned. And this is a sort of resource that uses computers at multiple institutions, universities, national labs, delivers millions of compute hours per day, and there's a public access point that anybody who's in the U.S. can apply to and get access. So this is something that no matter what you have locally, you should be able to access yourself. So this is just a note. Typically, any of these resources, whether locally or nationally, will be, there will be a variety of computers running. Most of them will be using Linux, but we have helped create Windows high-throughput systems for particular software. And often how these systems work is that they're using unused resources. So by that I mean you have computers that are dedicated for a certain task, but when they're not being used for that, jobs of various kinds can come in and run until the owner comes back. So a common example is running computations, running jobs on lab desktops while there's nobody around. Okay, so we have computers, but we need a little bit more than access to computers to actually run high-throughput computing workflows. If you imagine trying to start 1,000 simulations in parallel yourself manually by sort of logging into a bunch of computers and typing a command, that would be crazy. So most of these systems use a program called a batch scheduler, which runs on all the computers and sort of sees what computers are available, what jobs people have submitted, and then matches them up to run. And there's a lot of programs that do this. The one that we'll be talking about today, and that's run on a lot of high-throughput systems, is called HT Condor, which has really been optimized for these kinds of workflows, and also happens to be developed here at CHTC. So how it works then, in kind of diagrammatic form, this is an overview of the pieces here. You've got your computer, the place where you submit jobs, and all the computers that run jobs. And so very briefly, your first step would be to get an account on a submission or access point. Then copy whatever data you need to run your simulations or your jobs to that submission point. Creating a submit file, this is usually in the language of the scheduler that's being run, that describes what you want to do. In this case, it's going to be OpenSim jobs. Submit those to the batch scheduler on the submit node. Then the scheduler goes and runs them out on a pool of computers that are available to run jobs, often called worker nodes. And then they bring back the results to the submit node. So those are farmed out, results come back. And then you can collect the results and download them back to your own computer. So that's kind of how the whole system of batch submission works. And finally, besides computers, besides software, it's really helpful to have people help you get started in these methods. There can be a really steep learning curve. So at our center, we have my role, which is called a research computing facilitator, and there's two of us where this is our job, is to help people get started with using these methods and resources. There's a lot of resources online, there's workshops. If your colleagues are using similar methods, those are all places to learn from other people. Seminars like this, and so on. So if you have a good high throughput problem and are ready to get started, as I mentioned, it's always a good idea to check with your local IT and research computing staff to see if they have resources, computers, software, people for you. Otherwise, anybody can access the Open Science Grid through a public portal available at the University of Chicago called OSG Connect, and the link is there, and that's what Colin used for the demo today. And yeah, it should be as simple as applying for an account, getting approved, and getting started with running jobs. So with that, we're going to go back to the demo, which has hopefully made progress during this webinar so far, and I'll hand it back over to Colin.
Okay, so now back to the demo. So I'll just say that all of the materials for this demo and detailed instructions will be uploaded to our GitHub later today, so you can check out all of the files there. But first, I'll kind of give you an overview of what I actually launched onto the high-throughput computing grid at the beginning of this webinar. So we have a model that we built in OpenSim 3.3. It has a 6-degree of freedom tibiofemoral joint, an elastic foundation contact in the tibiofemoral joint, and then it uses what we call UW ligaments. So this is a custom plugin that we've written to include ligament models in this model. So what we ran is a passive simulation. So we used the forward tool in OpenSim, and we prescribed the tibiofemoral flexion angle from 0 to 60 degrees and then back to 0. And all other 5 degrees of freedom at the tibiofemoral joint are unconstrained, so they'll develop naturally as a result of the ligament and the contact forces. So we turned this into a probabilistic model. So what I did was set up a Monte Carlo analysis where I varied ligament stiffness. So each ligament in the model is represented as a normal distribution, the mean of which is the nominal model value, and the standard deviation is 30% of the mean. And so what I did at the beginning of the presentation was log into the Open Science Grid and launch these 3,000 simulations onto the grid. So in order to understand how this actually works to run simulations on the grid, you need to learn how to run OpenSim from the command line. So you're probably used to the GUI. So if we want to use the forward tool, you'd start with tools. You'd open up the forward dynamics tool. You'd load your settings file, and you'd click run. So in total, you'd have a model file. For us, we have contact in it, so there's 2 contact meshes. We have a ligament plugin, dynamic library, and then we have the settings file for the forward dynamic tool. So you can do this exact same process using the command line on Windows. So if you open a command line, then you could type forward, which means run the forward tool, load the ligament plugin, and then use this settings file. So it would be exactly the same results as what you got using the GUI. So this is on Windows 10 or really any Windows, but the Open Science Grid and most of the high-throughput computing grids out there use Linux. So you can pretty much do the same thing on Linux. So you can use a .sh file, and you can see here you can run the forward tool, load the plugin, and use the settings file. So also to set up this simulation, I had to generate the 3,000 models that we ran. So this we did using the MATLAB API for OpenSim. So you read in a nominal model, then we sample from the ligament distributions and write out thousands of model instances. And then you need to kind of set up a nice hierarchy of all your files so you know how to submit these jobs. So I start with a folder that I just call input data, and then I have a subfolder where I call it shared. So these are all of the files that are going to be shared among my simulations. So you'll see I had to, any files in bold are things that I had to add for doing high throughput computing. So we had to create this runjob.sh file that will command the simulation to start. And then I also had to recompile my ligament plugin on Linux because Windows and Linux don't talk nicely. So then the other thing you need to do is set up numbered folders that have the files that change between your simulations. So for us, it's just the model file that changes. So I have thousands of folders all numbered, and they all have their individualized model file. And then finally, you need to create the submission file that Christina talked about, which describes how this should be submitted onto the high-throughput computing grid. Next, you need to upload this to the submit node or the submit server. So there's a program called WinSCP that you can do this as a GUI. So you literally just drag and drop from your local computer here on the left into your submit server folder on the right. And so now we can check back in on our live demo. So I apologize that the color is not showing up well here. Let's see if I can make this any better for you. Nope. Okay, well, you saw earlier that I launched 1,000 simulations. So now we'll check in on those. So I can say condor Q and then my username, and it will list all of the simulations that I'm currently running on the Open Science Grid. So right now, all 1,000 of the jobs that I submitted are running, and none of them have completed. So we're not going to wait for these all to finish. I've already done this for you, so we'll just jump back to the presentation here. So normally you would need to collect your results when they finish and download them using the same WinSCP software. And then now we can actually look at these results. So for a batch that I ran earlier of 3,000 simulations, you're looking at the knee adduction angle over the simulation for all 3,000 here. And then you can run whatever analyses you want on them. So I'm plotting the mean and 95% confidence intervals for you. And now you're really set up to do this on your own. So the last thing that we'll kind of finish with is the challenges with high throughput computing. So first, your simulations need to be Linux compatible. So if you're using OpenSim 3.3, we already have it installed on the Open Science Grid for you. So that's actually pretty much set up. If you're doing some custom things on your own, this is something that you'll need to figure out. You really will start running into a big data management problem. So you'll ask, like, well, how many simulations can I run on these high throughput computing grids? And really, it's as many as you want. It's just a matter of how much time you're willing to wait and how much storage you have. So when I generated these 1,000 models files, that's half a gig. And then when I collect simulation results for 1,000 simulations, that's 2.5 gigs. So you can imagine as you scale this up, you actually do start running into problems with file transfer and just where you're saving your data. And the last thing is failed simulations. So sometimes with these Monte Carlo analyses, you end up sampling a combination of parameters. For example, if all of the knee ligaments ended up being very soft or compliant, and the knee ends up dislocating in my simulation, well, I don't have a monitor or GUI to look at that simulation in. So when I look at all 2,000 results coming back, one of them won't make any sense. So you do need to kind of watch out for things that will cause your simulations to fail. So in summary, what we've presented today is our enhanced knee model and simulation technique. And this is something that we do in custom code right now, but we're working on an OpenSim plugin, and we're hoping to release it in spring 2017. And maybe we'll have another webinar for that. We showed you how high-throughput computing can enable stochastic simulation and how we've used that to answer research questions. And then we've shown that you can use high-throughput computing in your own research. We have OpenSim installed on the Open Science Grid, so you'll have to make an account and get approved for it, which will take a little bit of time, but aside from that, you're ready to go. So with that, we'd like to acknowledge our funding sources and our collaborators. And we'll hand it back to Jen and Joy.
Thanks, Colin and Daryl and Christina, for a great talk. It was really cool to see the model, the applications, and also learn how we can apply similar techniques to our own research. We'll now go ahead and open up the Q&A session. So next slide, you have the directions. Yeah, so I think the interface has changed, may have changed a little bit, but you need to find the Q&A interface and go ahead and type in your question and make sure you select to ask all panelists. So with that, yeah, we'll go ahead and open it up to questions. Go ahead and type those questions in. While we're waiting, I have a couple questions. The first is, so you were talking about is your future directions looking at parametric modeling, and you had some nice plots where you showed the variation of some value of interest as a function of a specific parameter like gastrocnemius force or ligament stiffness. Are you able to look at interactions between different parameters as well?
Yes, we are. So as we've been kind of getting better at high throughput computing, we've been doing more and more complex analyses. But so originally we kind of just varied one parameter and looked at how that affects the results. as you start varying more parameters, you need to start running more simulations. So it kind of scales up the problem that you're looking at. But there are some more complex analyses you can do with Monte Carlo, such as Sobel indices. And those will let you look at not only the sensitivity of your simulation results to a single parameter, but also the interaction effects. So it's kind of a more complex statistical method.
Mm-hmm. Cool. And then my other question was, so you guys talked about what kind of problems were good and not ideal for using high throughput computing. Do you have, have you guys thought about some more examples of what might be good types of problems to use versus ones that, wouldn't be helped out so much by high throughput computing in the specific biomechanics space?
I guess so jobs that don't work well for high throughput computing would be ones that need like parallel processors. So if you're doing some sort of a high performance computing where you're running a really complex finite element model and lots of things need to talk to each other and are done in parallel, getting multiple processors on a high throughput computing grid is possible but not easy. So you really want kind of an independent simulation that can run on one processor in a reasonable amount of time.
Right, so the other example in like the OpenSim space would be if you had a muscle that had 1,000 muscles and it was slow because you had 1,000 muscles. Using high throughput computing probably wouldn't help you out too much because there's interactions between the dynamics of all the muscles in the system.
Yeah, this is Christina. I would say the key is whether your method requires independent calculation. So yeah, if the 1,000 pieces of the simulation all impact each other, and that takes days and days, that would not be so good for high throughput computing. But in general, I'd say any sort of probabilistic methods, kind of as Colin and Daryl described, anything requiring randomness, for people using Monte Carlo approaches, anything where you want to do parameter tuning, that can be a good application where you can just sort of sweep a bunch of parameter combinations that you'd like to try. And then doing straight up data analysis if you have a bunch of independent data points where you want to apply the same sort of analysis pipeline. So I'm not a biomechanical expert.
The other application I can think of is doing shooting optimizations if you're using an algorithm like CMA that optimizes by randomly sampling your search space and doing running simulations at each of those points, right, and then comparing all the results would be another good application of high throughput computing.
I'll add one thing in that most OpenSim style simulations will work very well for high throughput computing. The places that you will run into issues is kind of unstable simulations. So if you've gotten CMC to run where you've tuned all of your parameters so it just works one time, and then now you want to start varying these parameters, and when you vary the parameters, the simulations start failing, that's the kind of problem that won't work well for high throughput computing. So you really want kind of a stable simulation that you can vary parameters and you won't cause failure.
Right, yeah, that's a good point too. So now we'll move to some questions from the audience. This is a question from Tran V. Doe. So is there any way to simulate abnormal structures of the body? For example, with the knee joint, could you simulate if a ligament were disrupted, the influence of that ligament disruption on knee movement?
Yes, you certainly can. And we've done some of those type of simulations. So we've done some work looking at ACL deficiency and how that would affect both coordination and internal knee mechanics. And those that works fairly well with the model to run those types of things. Are there any other examples? We've also done some surgical simulations where you're altering the musculoskeletal structures and then using the model to predict the effect. And That's particularly interesting when you look at surgical factors like the example that Colin showed in the ACL graft placement. We're doing some of that also in regards to pediatric gait treatments, so some of the orthopedic decisions they make there and how that might affect knee mechanics during walking.
Great, thanks. So now a question from Mohammed Sadatsi that's a follow-on from our earlier discussion about the types of applications for high-throughput computing. And his question is, so is it possible to run smart optimizations in which after each iteration the results are compared?
So that's a great question. It depends a lot on how frequently you want to do that. If the iterations are kind of short and you want to do like an iteration and compare and then iterate and compare, that's more of a process where they all need to be communicating with each other. And if that's quite quick, that's less amenable to high throughput computing. We have worked with people where it was more like they were just running a bunch of things in parallel and then comparing at the end and then maybe doing 1 or 2 more rounds. And that would work with high throughput computing. There's a workflow manager that you can use to run jobs kind of in a specific order. But it's not meant, a single job that you submit should usually be at least a couple minutes to be worth the overhead of scheduling it on the system. And so it just really depends kind of the scale and speed and size, all those words, of your particular problem.
Okay, that makes sense. I have a question about the Open Science Grid. So I was wondering, can you use the Open Science Grid to operate on data that's not public data? You know, is the data secured, or you know, how is that handled?
That is also a good question. The people, because I work at the university and we send people to the Open Science Grid, but I don't manage it myself, or we don't manage it here specifically either. The people to talk to would be the folks at the Open Science Grid. OSG Connect, their support, might be able to advise on that. It's certainly a closed system in that you have to log in to access it and that kind of thing, but you are sending jobs to computers at different locations that may have different levels of security. So I'd say it depends on the sort of restrictions around your data. We've definitely had people use de-identified medical data on our systems and on the Open Science Grid, and to talk to the OSG folks and see what sort of recommendations they have for handling data on that system. Yeah, the data is deleted from the machines where the jobs ran. So it's not sort of like you're just leaving data everywhere.
Yeah.
I think it's fairly secure as far as these systems go, but it would definitely be something to talk to your IRB and the OSG people. I don't know if Colin or Daryl have anything to add there.
I was just going to say we can look into it and post the concrete answer later.
Yeah.
Cool. That sounds good. And then another one about Open Science Grid that we'll see if you guys know the answer, and otherwise we can follow up.
Yeah.
Is whether the Open Science Grid is available to researchers in Europe. That's a question from Antoine Felice.
Let's check and get back to you. I'm pretty sure it's funded by the NSF, so I think there's some sort of restriction there. But if you have a collaborator in the States, there might be some workarounds as well.
Gotcha.
But I can check and get back to people.
Okay, that sounds great. Yeah, we'll send up a follow-up email to the webinar that will have a link to the papers and projects that you guys talked about, and we can have some answers to these questions too, and links to Open Science Grid and everything as well. So if there are no further questions, we'll go ahead and wrap up the webinar. there's a couple more slides if you guys could click through those for me. So we took care of questions. So OpenSim and the webinar series are supported by several grants from the NIH, including an NIH grant that funds our National Center for Simulation and Rehabilitation Research. So we definitely want to acknowledge all of our funding sources that make OpenSim and this webinar series possible. Next slide. And to close, I really want to, again, thank our speakers for a really interesting and valuable talk. It inspired, new ideas for me, and I'm sure new ideas in the audience as well. Thanks to the audience for all the great questions. You can find more information about OpenSim, other upcoming events, and other resources from the OpenSim community on our website, including future webinars. We'll have a survey that will pop up in a window at the conclusion of the webinar. Please fill this out to let us know how to improve the webinars and give us ideas for upcoming topics. And again, thank you everyone for participating. Thanks again, Daryl, Colin, and Christina for a really great talk. And we hope you'll all continue to stay involved with OpenSim.